So, welcome all of you to our next set of lectures on the properties of the atomic nucleus. So, this is a good time for us to take stock of what all we have learned during these lectures on the so called modern physics, which was actually initiated by the seminal work of Planck in 1900. So, we started with the problem of the black body radiation and then moved on to the concept of the photon, which was used very effectively by Einstein to explain photoelectric effect. So, we pointed out the revolutionary character of the concept of the photon and how Einstein was able to use that to understand the otherwise very difficult concept of the very difficult results of photoelectric effect, the experiments performed by Hertz, Lenard, etc., etc. From there, we moved on to the properties of matter, I mean microscopic matter, and we started looking at the structure of the fundamental constituents of matter, and we discussed both matter waves due to de Broglie, which found a brilliant experimental confirmation in the experiments of Davison and Germer, and then of course the Bohr model. The Bohr model actually was able to explain so many empirical laws involving the so called Blackett lines, Paschen lines, Bartlett lines, and it also was able to give us a fairly good picture of periodic table, which was empirically arranged by the chemists in order to understand chemical properties. The precursor for the Bohr model was of course the Rutherford model. Rutherford did his great experiments by scattering alpha particles against gold foil, and he concluded from his experiments that most of the atom is empty. In fact, almost all the mass is concentrated in a very tiny region in the atom, about 10,000 times smaller than the size of the atom, and then the electrons are orbiting at a large distance, that is compared to the size of the region where the mass is distributed in some kind of a planetary orbit. Bohr was able to pick up on these things and develop the Bohr model, from which he was able to explain the spectroscopic data. If you combine the Bohr model together with the Pauli exclusion principle, which I briefly described to you, then we would be in a position to understand the periodic table qualitatively. Of course, understanding the periodic table fully is a really difficult task, because we have to switch on the interaction between the electrons, we have to switch on the effect of what is called as the spin orbit coupling, so on and so forth. We need not worry about that, but a qualitative understanding of the periodic table, for example, why there are these noble gases or the inert gases, why there are these halogens, why there are these alkalis, what are their properties, these are some things which we can actually understand. From there, what we did was to turn on our attention to the region in the atom where most of the mass is distributed. So, let us start with a description of these things. We have discussed a part of it in our previous lecture, but at this point it bears some repetition. So, let us see how it goes. So, what we do is to start with a brief description of the Rutherford model and then describe the famous experiments of Chadwick. That is what we would like to do. So, we are now going to study the properties of the atomic nucleus. So, remember what Rutherford showed us was that there is a central region where most of the mass is distributed, and then if you look at hydrogen atom, for example, my electron is orbiting in this, let us say, circular orbit. So, to give you an idea of the scale, this length scale is of the order of 10 to the power of minus 8 centimeter, 10 to the power of minus 10 meter, that is of the order of it. And what the Rutherford experiment told us was that this region is of the order of 10 to the power of minus 15 meters. So, as I told you, the region where most of the mass is concentrated is in a very, very tiny region. It is about 10 to the power of minus 15 meters. And now the question that we are going to ask is, how do we resolve this structure? So, in other words, what I want to do is to zoom it, let us say, through a microscope, and then I want to see what the constituents are. This is the question that we have to answer. We know that my electron is a negatively charged particle, and if you look at a more complicated atom, there are more and more electrons in various orbits. Therefore, for surely this contains positive charge. This contains positive charge. Now the question is how the positive charge is distributed in this small region in this space, and whether it is only positive charges or whether there are other particles also which is in this region. And this tiny region is what is called as a nucleus. And we are interested in the properties of this nucleus. To be sure, we know the property of at least one nucleus, and that is in the case of the hydrogen atom. So, in the case of hydrogen atom, you have the nucleus, you have the electron, and this is carrying a positive charge. So, and we call it as a proton. So, for our purposes, the completely ionized hydrogen atom, the positive part, is what is called as a proton. And there are some interesting properties which you people know, that the mass of the proton is roughly 2000 times the mass of the electron, and equally importantly, the charge of the proton is identically equal to the charge of the electron. Charge of the electron, that means atom is overall neutral. Now, atom is overall neutral not only when we look at the hydrogen atom. In fact, it is neutral for all the atoms in the periodic table. We have about 100 atoms, 100 and odd atoms which are listed. Therefore, we can conclude that if you look at an atom with Z number of electrons, then there are Z number of protons in its nucleus. So, for example, let us look at the helium atom. What we are going to find, if you look at the helium atom, 2, so this is the Z number of electrons, let us say, at this particular point. So, you have the nucleus and you have 2 electrons which are orbiting the nucleus. So, we know for sure that Z is equal to 2 here as well. This is the number of protons. So, if you go by our mass relation, then mass of the helium atom should be roughly twice the mass of the hydrogen atom. If my nucleus consisted only of the protons, but this is incorrect, what we have is that it is roughly equal to 4 times of the mass of the hydrogen atom. So, this suggests that there must be other particles which are sitting inside the nucleus. What I am giving you is a very brief summary of the discussions that we had in great detail in the previous lectures. That is what I am giving you, and these extra particles were what were called as the neutrons. So, to just refresh your memory, what we have to do is to look at the slides which I showed you in the last time regarding the famous experiments of Chadwick. So, let us start with them. So, here is a picture of Chadwick. here is a picture of Chadwick, who did these seminal experiments. Maybe I flashed it to them in the previous lecture, but never mind. So what Chadwick did was to bombard light elements such as boron and beryllium with alpha particles. So the point that you have to notice at this stage is that when Rutherford bombarded the atom with alpha particles, they had a few kilo electron volt range, let us say. But here what we have is alpha particles coming with energies of about a few million electron volts. Is that okay? So they are much more energetic compared to the alpha particles from that bombarded the gold foil. And where did you get these alpha particles from? You got them from the radioactive decay of polonium, and there the energies are typically of the order of 5 MeV. Now when you bombard them, essentially what happened was that the nucleus got completely shattered, it broke, and what you do is to apply electric and magnetic fields to isolate the particles which are charged from particles which are not charged. That is the whole idea. So this experiment was performed by Chadwick, and what is it that Chadwick found? Chadwick found that, of course, a large number of protons came out. That should be equal to the number of protons in the boron atom or in beryllium, let us say. And then he also found that there was a neutral radiation. This neutral radiation had very great penetrating power. So what did they do? They made the neutral radiation also bombard some other target, and they found that they themselves could eject protons and electrons. That is what they found out. And therefore the big question was, what was this neutral radiation consisting of? It is interesting to know that by that time, by the time these experiments were done, there was already the concept of photon which was firmly established. Compton had given his explanation for the Compton scattering effect by looking at what? The momentum of the photon and the energy of the photon. So both Pierre Curie and Marie Curie, husband and wife couple, they first actually wanted to identify these neutral particles with the photons, very highly energetic photons. However, if you look at the atomic masses which I showed you just now, it suggests that it should not be photon, but it should be some other particle whose mass must be roughly the same as the mass of the proton. That is what it is going to suggest, and this is exactly what Chadwick did. Chadwick imposed energy conservation condition, momentum conservation condition, and he knew the maximum energy with which a photon would be able to come out of a nucleus, and he argued that there could not be photons, but it has to be a new kind of a particle. And by a careful analysis, we don't have time to get into that. What is it that Chadwick found? Chadwick found that the new particles actually were very close in mass to that of a proton. So as I am pointing out there, mass of the neutron, he called it as a neutron, it's about 1.15 times the mass of the proton. That was Chadwick's estimate, and today very careful experiments show that it is about 1.001 times the mass of the proton. That is the current value, and given the experimental conditions of those days, this is a remarkably good experiment. That is what we have. So now what we will do is to accept the Chadwick explanation, and we shall go on to understand how we can start with the Chadwick hypothesis of the existence of the neutrons in the nucleus, the so-called atomic nucleus, and use that to further understand the properties of the nucleus. So you should remember that physics started something with a human scale, about a meter or a 2 meters, let us say, order of magnitude. Then you go to a micron, which is the size of a dust. Then we went to atom, which is about 10 to the power of minus 8 centimeter. So another 4 orders of magnitude down. Now we are going another 5 orders of magnitude down to the very structure of the atomic nucleus. That is the most important thing. Now if you look at this slide, let us summarize what all we have learnt from all the experiments that we have discussed very briefly so far today, and from the earlier experiment from our earlier discussions where I discussed them in great detail. So what is it that we find? The atomic nucleus consists of 2 kinds of particles. What are they? The protons, which have positive charge, and neutrons, which have negative charge. And what is the most important piece of information for us at this particular time? The mass of the proton is roughly the same as the mass of the neutron. In fact, the mass difference between them is 1 part in 1,000. So, if I were to write, I would write it in a following way: mass of the neutron minus mass of the proton. So, that is what I want to write, divided by, let us say, mass of the proton, take the modulus value, this is of the order of 10 to the power of minus 3. This is no accident. In fact, later when you study physics, you will find that this particular idea, together with other properties of the nuclear forces, was responsible for introducing the concept called isospin. We are not going to get into that. Now, let us go back and look at our slides. So, if you look at your slide, what is it that we are finding? I said that the mass of the proton is roughly the same as the mass of the neutron. That is what we found. Now, there is no evidence for the existence of electrons in the nucleus. This is very, very important. This you have to remember, because later when we discuss the radioactive decay, for example, a neutron is not a stable particle. It decays into a proton and an electron and an antineutrino. You should not think that my neutron is containing an electron. That is not true. That is something that we have to remember. So, coming back to the slide, there is no evidence for existence of electrons in the nucleus, and of course, there are always as many protons as there are electrons orbiting the nucleus. This is a qualitative summary of whatever we have done. Now, what we do is to look at it more quantitatively. So, as I told you, the big question from the viewpoint of Curie hypothesis and Chadwick's experiment is, what about the number of neutrons? How many neutrons are there in a given nucleus? And secondly, chemists who studied all the elements in great detail, and then starting with Mendeleev, who arranged all the elements in a periodic table, they had these concepts of isotopes, isobars and isotones. So, from this new understanding, how do we understand isotopes? For chemists, isotopes were different elements having the same chemical property. But in what sense are they different if they have the same chemical property? In a similar manner, what are isobars and what are isotones? So, these are matters of jargon, empirical jargon when it comes to chemistry, but starting with physics, now we should be able to get a precise understanding of that, and let us see how it looks like. So, this is the periodic table, and in the periodic table, if you were to look at it very carefully, you find that each element is going to come with a large number of so-called isotopes. So, our idea is that we want to understand qualitatively, not quantitatively, periodic table completely. Let me explain what I mean by that. When I speak of the periodic table, there are two aspects. One is the chemistry aspect, which can be understood qualitatively by appealing to the Bohr model and of course quantum mechanics. Then there is the positive nuclear aspect. You can call it nuclear chemistry or nuclear physics. That is something that we have to understand. If you understand the core, that is the nucleus, and if you understand the orbiting particles, that is the electrons, then we have understood all aspects of periodic table. That is what we would like to do, and let us proceed. First, we need a notation. So, the notation that I am going to employ, I believe that is the same notation which is employed in your 12th standard NCERT textbook, let us say. The nucleus, we are not going to look at the atom now, will be represented by the symbol AXZ, and have defined all of them in this slide. So, there are three symbols which are as characterizing every single nucleus. If you hold both A and Z fixed, then X is called a nuclide. So, please remember the word X is called the nuclide. So, first X is the nucleus. So, what are the examples of nucleus? You have hydrogen, carbon, phosphorus, chlorine, iron, etc., etc. That is what it is. Now comes the symbol A, which is at the top, left top. A is the total number of protons plus neutrons. So, in chemistry, it was called atomic weight. Is that okay? But here it is the total number of protons and neutrons, and there is a jargon again. If you don't want to make a distinction between a proton and a neutron, that is, if you want to use a common word which describes either proton or neutron, then what do you call it? You simply call it a nucleon. So many times I will say a nucleon is roughly 2000 times heavier than an electron. What do I mean by that? That means whether you take a proton or a neutron, it doesn't matter. Both of them weigh roughly 2000 times the electron that we have. That is what we have in our mind. So A stands for the total number of protons plus neutrons in a nucleus, and Z stands for the total number of protons, and that is what is called as an atomic number in chemistry. Now atom is completely neutral, therefore Z also stands for the total number of electrons in an ionized, non-ionized atom. Of course, you can take an atom and you can ionize. You can take helium atom and you can knock off one electron. You can take helium atom, you can knock off 2 electrons. That is not what I am referring to. If you look at a neutral atom, then this Z stands for both the number of protons and the total number of electrons. And then of course, A minus Z is the total number of neutrons. So this compact notation AXZ tells me everything about the nucleus, nuclide if you feel like, and also about the atom, provided it is not ionized, provided it is in the neutral states. Now once you did that, whatever is empirical now becomes a matter of fact. You are able to understand it completely. And what is that? If you take 2 nuclides with the same Z, they are called isotopes. If you take 2 nuclides with the same A, they are called isobar. So bar is like weight. Is that okay? And 2 nuclides with the same A minus Z, that is with the same number of neutrons, they are called isotones. Isotones are not very important for us either in chemistry or physics, but isobars and isotopes are both very, very important, and let us give some examples. So a very good example of isotope, in fact a set of examples for isotope are nothing but the well known hydrogen, then you have deuterium and you have tritium. So how are we going to distinguish them? Now look at the notation 1, 1H. That means hydrogen atom has what? A equal to 1, Z is equal to 1. So what does it tell you? It tells you that the number of protons is equal to 1. The number of protons plus neutrons is equal to 1. Therefore, the number of neutrons is equal to 0. That is what it tells me. Now, if you look at the next isotope 2H1, what is it telling me? It is telling me A equal to 2, Z equal to 1. That means there is 1 proton, that is my atomic number. My atomic weight is equal to 2, that is what I have. That means number of protons plus number of neutrons is equal to 2. Therefore, there is 1 neutron. And of course, the next one is tritium in a similar manner. It has also 1 proton, but its atomic weight is 3, which means it has 1 proton and 2 neutrons. Now we understand why they are called as isotopes, because all of them have the same number of protons. Therefore, apart from very, very small corrections, if you look at the chemical property, each of them has only 1 electron which is orbiting, whether it is the hydrogen or deuterium or tritium, that is what you are going to find. Therefore, what you have is they have similar chemical properties. In a similar manner, you can look at helium and tritium. You can look at 3 helium, which consists of 2 proton and 1 neutrons, and tritium, which consists of what? 2 neutrons and 1 proton. Both of them have the same atomic number. So let me write that for you here. So I want to write, for example, 3 helium 2 and 3 tritium 1. That is what I want to write. So here my A is equal to 3, my Z is equal to 2, and here also my A equal to 3, but Z equal to 1. Now you see, this tritium is an isotope of my hydrogen atom. That is why I use the same notation H, because both of them have the same atomic number 1, but it is an isobar. So it is an isobar of 3 helium, because both of them have the same atomic weight. That is, they both share the sum of number of protons and number of neutrons inside the nucleus. So, when it comes to mass, it is the isobar. When it comes to the number of protons, it is nothing but the isotope. That is something that we have to remember. Okay. Now, we have disposed of with the jargon. Now comes the next question as to what the size of this nuclei is. Now, this is a very, very important question for us, on which I am going to spend quite some time. So, what we are interested is in the size of the nucleus, of an atom. So, first comes the rough scale. From Rutherford experiment, let us say. So, if I look at the volume or the radius, it really does not matter. Radius of the nucleus is of the order of 10 to the power of, let us say, minus 14 to 10 to the power of minus 15 meter. So, that is what I have. Now, what I want to do is to actually sharpen it. So, what do I want to do? I want to pick up a very, very powerful microscope, as I told you, which will magnify the size of the nucleus. So, what does it do? It magnifies the size of the nucleus, and I want to be able to estimate its radius, assuming it is spherical for the time being, in a more precise manner. That means in the units of 10 to the power of minus 15 meters. That is what we want to do. And in order to do that, what we have to do is to appeal to the experiments. Now, never mind if you cannot see this figure completely, but what I would like to convey to you, this is exactly what I discussed with you when I was looking at the structure of the atom, is that this is a recent experiment, relatively recent experiment performed in 2008, and what you do is to look at the scattering of the electrons, mind you, electron, not of alpha particles, against various nuclei. So, you have these nuclei, for example. The bottommost is lead with an atomic weight of 208. The one above that is oxygen 16. The one above is 99 zirconium. So, these are heavy nuclei, and what you do is to send electrons which are fairly energetic. So, how energetic are these electrons? The energy of the electrons is of the order of, for example, 500 MeV, 374 MeV and 300 MeV. These are really energetic electrons, but you take care to see that the scattering is elastic. You know the difference between elastic and inelastic scattering. What happens in an elastic scattering? The body is intact, both energy and momentum are conserved, nothing goes into the internal energy, no energy is lost. In an inelastic scattering, something can go into an internal energy, or the energy can get lost. And how does it happen in the case of electron atom scattering? At this energy, let us say 500 MeV, it can knock off a proton, it can knock off a neutron, so on and so forth. Nothing like that happens. My initial state is the nucleus, and the final state is the same nucleus. That is what we are interested in. And what you do is to look at what is called as the scattering cross section. That is, you look at how many electrons are scattered in different directions. So, here is the experiment. Here is my nucleus, let us say 208 Pb. That is what I have. So, let me show it to you clearly. This is my 208 Pb. Here comes the beam of electrons of, let us say, some energy, even 50 MeV should be okay with us, and they get scattered. And we should assume that they are getting scattered inside the nucleus. We are not interested in these fellows, we are interested in those that are getting scattered from within the nucleus, because I want to see the structure. So, I am interested in this, I am interested in this. Now, what I do is, I put a detector here, and count the number of particles which are coming as a function of what? Scattering angle. So, let me show that again here in a much neater figure. You have the target. So, here is an electron which is coming like this. So, this is my 0 scattering angle, this is my theta, and I am asking how many electrons are coming out in an angle theta. So, in fact, I can call it as n scattered at an angle theta. This is essentially going to give me information on the structure. That is what this experiment is going to be all about. Now, what do? I look at this carefully here. So, you have to look at this slide now. Let me show you this slide. If you look at this slide, you see that as I look at larger and larger scattering angles, the cross section, that is the number of particles that are getting scattered, is falling very, very rapidly. This is a logarithmic scale. This is not a linear scale. 10 to the power of minus 1, 10 to the power of minus 2, minus 3, minus 4, so on and so forth. It falls off very rapidly. But the important thing is that when it falls off, you see there are these oscillations. There are these minima, maxima, minima, maxima. And if you people remember the wave optics that you studied in your optics course, whenever there is a diffraction, for example, you are going to find minima, maxima, minima, maxima. And what did Davison-Germer and de Broglie teach us? Davison-Germer and de Broglie taught us the most important thing about electrons, that is, not only do they behave like particles, they also behave like waves. So, now if you imagine that actually this is like a diffraction pattern which is coming because of the scattering of these waves, that gives me an idea of the radius. Just as there you get an information on the, for example, the properties of the slit when you look at the diffraction, here you are going to get information about the radius or the size of the nucleus. That is the great experiment of these people. Of course, there is a long experiment starting with the work of Hofstadter. We do not have to get into that. So, what I will do is, since we can't get into a very, very detailed analysis, what we will do is to convert it into a statement of charge density. How does the charge density behave? So, I am going to convert the information coming from the scattering cross section into charge density, and here is the important thing. So, you make use of these diffraction patterns and you will find that the charge density is roughly constant and falls off very rapidly. That is what you are going to find. I am using the word very rapidly, I am not using the word abruptly. That is something that you have to remember. And this is not the result of a single experiment. Actually, it is a result of a large number of experiments. These are the names of the groups: G2, NL3, FSU, DD, SLY, etc., etc. This is on oxygen 16. And all these experiments agree that my charge density roughly remains the same and it falls off very rapidly. That is what it is going to show me. And this is in the unit of 10 to the power of minus 15 meters. That is what I have shown here, in 10 to the power of minus 15 meters. So, I am able to break this into that many units, 1 into 10 to the power of minus 15, so on and so forth. If you go to a heavier nucleus, let us say 90 zirconium, everybody remembers what 90 stands for. That is the atomic weight, the number of protons plus the number of neutrons. You see, again my charge density roughly remains the same for a large distance and it again falls off. And if you go to lead nucleus, the charge density remains roughly constant and again falls off. And what is the most important thing? The range over which my charge density remains increases. I move from oxygen 16 to zirconium 90 to lead, and now we are interested in the relation between the atomic number, the atomic weight and the distance over which my charge density remains the same. Now, if you assume that the neutral particles are also distributed uniformly inside the nucleus, namely my neutron, that means my mass density is distributed uniformly over the nucleus. However, this this rapid fall, which is not an abrupt fall, tells me that my nucleus does not have a fixed boundary. It slowly tapers off. What is an example for that? A very good example is our atmosphere. If you imagine that earth means only solid earth, and if you, for example, ignore the Mount Everest or the valleys, let us say Grand Canyon or whatever, then Earth is a solid with a fixed radius. That means it has an abrupt ending. But rightly speaking, we should also include the atmosphere in the Earth. Now we know the Earth does not have a fixed radius. As you go higher and higher, what happens? The pressure keeps on falling, and therefore the density keeps on falling. And if you go about 200 kilometers above, probably there is practically nothing, but we can never ascribe a definite boundary to the Earth when we include the Earth. In a similar manner, if you look at these experiments, you see that you cannot ascribe a definite boundary. But if you look at a benchmark, let us say half the distance at which the charge density falls off to half, that can be called as the nuclear size or the nuclear radius. So if you did that, what we are going to get is a rough idea of what the charge of the nucleus is, and that information can be very succinctly captured in this. Please remember, the results that I am showing you are results which are based on a large number of experiments, a large number of empirical observations, and all of it can be summarized in this slide. And you see that of the two parameters A and Z, only one parameter plays a role, namely the atomic weight and not the atomic number. This is very important for us in studying the properties of the nuclear forces, and we will come to that in a while. That is something that we have to do. So what we have to do is to look at this structure. What we are going to assume is that my nucleus is roughly spherical. In fact, more careful experiments also reveal the ellipsoidal nature of some of the nuclei. We are not going to get into that. The important point is that the radius goes like 1/3 of the power of the atomic weight. So if you assume that the mass is uniformly distributed, then mass goes like linear function of A, and volume also goes like a linear function of A. Now what is it that you are finding? There is an empirical parameter R naught, and this R naught is given by 1.25 into 10 to the power of minus 15 meters. So we are looking at everything in units of 10 to the power of minus 15 meter, and there is a special name. Just as 1 angstrom is 10 to the power of minus 8 centimeters or 10 to the power of minus 10 meters, this has a special name after Fermi, the great Enrico Fermi. So 10 to the power of minus 15 meter is 1 Fermi, and just to tell you that this formula is empirical, my radius of the proton is 0.85 Fermi. It is not exactly 1.25. That means this formula does not hold very accurately for a proton. It is some kind of a rough estimate of what the size of the nucleus is. So what we have is the following relation, which is very important for us. And from this, you can make a whole lot of estimates. So what is it that I wrote? R is equal to R naught A to the power of 1/3. So R of A, and mass is given by m naught into V. Why is it so? Because my mass is the density multiplied by volume. We already said that this density is a constant. Therefore, this is rho constant into R cubed of A, which is rho constant into R naught cubed, which is another constant, into A. So this is my m naught. That is what I have. This is very important for us. And from this, you can estimate a whole lot of things. So for example, if you are given radius of, let us say, 16 O, we should be able to get let us say radius of 12 carbon. We should be able to get that. How do I do that? Radius of 16O is R naught into 16 to the power of 1/3. And radius of 12 carbon is R naught. So let us say I know this. into 12 to the power of 1/3. What do I conclude from this? From this I conclude that radius of 12 carbon divided by radius of oxygen is nothing but 12 by 16 to the power of 1/3. So, experimentally if somebody measured this, that means if somebody determined R naught, you will conclude radius of 12 carbon is 12 by 16, that is 3 by 4 to the power of 1/3 into radius of 16 ohm. And this is very, very close to 1. Whatever. So, there are many, many minute changes, but this is something which you can actually experimentally verify. In fact, this formula was derived by looking at the experimental data. So, this is a very, very important thing for us. So, what do we know about the nucleus so far? Protons, neutrons, both of them have size of about 10 to the power of minus 15 meters, that is what we have, and the nuclear size is R naught a to the power of 1/3. Notice when I am writing a to the power of 1/3, that means I am sensitive to changes in the scale of femtometer. Fermi. So, you can read Fm as either femtometer or Fermi, because Fermi stands for a femtometer. Now, that means the initial statement that I made, my proton and neutron have roughly the same mass, that won't work out anymore, because now I should be equally careful about the masses of the nuclei. So, what we shall do is to go on to the next topic of great interest, and that is masses of nuclei. In fact, the fundamental problem in nuclear physics is to determine the mass of a nucleus, the magnetic momentum of a nucleus, the total spin of a nucleus, and how the orbits of electrons and protons inside a nucleus are there. What is the complete structure? And that is a very, very difficult problem, but we do not have to worry about it at this particular stage, because our interest is actually in obtaining a qualitative understanding with basic ideas of scattering, wave particle duality, uncertainty principle, so on and so forth. That is what we are interested in, and in order to understand that, we need a break. That is a very, very important thing. And what is that break? That break is of relativity. This break is that of relativity, but then you know, and I am equally conscious, that you are not going to study relativity in any of your courses. But never mind, if you look at your 12th standard NCERT book, the famous mass energy relation is given there. So, what we can do is to try to get an understanding, get a feeling of how you get the mass energy equivalence, and what are the changes responsible for that, and how to formulate it. We are not pretending to teach relativity to you, but we are just giving some basic facts so that you get a better feeling for what is happening. So, let us start with some simple relations, and let me give you a few matters of fact, and let me collect them. All of you would have read popular books on relativity, heard popular lectures on relativity, and what is the first thing that you know? The first thing that you know is that no material particle can move with the speed of light, let alone exceed the speed of light. Now, notice I carefully use the word material particle. What do I mean by material particle? electron, proton, neutron, atom, nucleus, molecule, earth, ball, whatever. What is an immaterial particle then? Whatever we thought was waves. For example, electromagnetic waves when quantized become photons. Of course, electromagnetic wave moves with what? The speed of light, and therefore photons also move with the speed of light. So, we want to make a distinction between that kind of a particle from the material particles, whatever we understood from classical physics. Therefore, we say no material particle can move with the speed v greater than or equal to c. However, there is no restriction on the energy that a body can possess. Why? If I keep on pumping energy, the energy of the body keeps on increasing. There is no restriction. So, we have a problem. And what is the problem? Speaking classically, let me come back to this. If I look at, for example, Newtonian case, P equal to mv and E equal to half mv squared. That is what I have, where v is my speed, velocity, if I put a vector sign. Now, if I take a particle and put it a uniform field, what do we know? My v equal to at. Therefore, my v will continuously increase and eventually exceed the speed of light. That is the Newtonian case. But Mr. Einstein tells us, or even better, experiments tell us that no material particle can move with a speed greater than that of light. That means this expression is wrong as it is written. Now, why is it that v is equal to at? Remember, a is the acceleration. So, what you do is to write dp by dt is equal to m dv by dt is equal to f. That is what you are writing. And then you write a is equal to f by m. That is what you write. And the most important thing is you take m to be independent of speed. Independent of speed, that is what you do, and therefore you will write v of t is equal to f by m into t plus some v naught. That is what you write. So, this integration, that is the most important thing, assumes that my m is independent of speed. But if my m is independent of speed, this can become greater than c for sufficiently large values of time. So, what do we conclude from that? If you come back to this slide, what you will notice is that my momentum cannot be given by mv, where m is independent of speed or velocity. But for the same token, my energy also cannot be given by E equal to half mv squared. So, the solution to this problem, that I can keep on increasing the momentum of a particle, that I can keep on increasing the energy of a particle, but I cannot keep on increasing the speed of a particle such that it hits c or exceeds the value of c, is that my inertia or mass should depend on the speed. This is the basic idea. So, once we admit that, let us assume that Mr. Einstein did all the hard work for us. You make your inertia as a function of velocity. So, when you make your inertia as a function of velocity, the new definition of m at any velocity will be given by m naught into 1 over root of 1 minus v squared by c squared. So, there is an additional factor 1 over root of 1 minus v squared by c squared. That means that the usual notion of inertia which Newton gave us holds only when v equal to c or when v is very, very close to c. So, let us come to that. What is it that I wrote? I wrote m of v is equal to m naught 1 over root 1 minus v squared by c squared. Now, if v is very small, what does v equal to c small mean? V by c is much smaller. Even the earth, which is going around the sun with a very, very great speed, even for that v by c is very, very small. You can verify that. Speed of the earth is about 30 kilometers per second or whatever. You can make a binomial expansion, and what do you get? you get m of v is approximately m naught into 1 plus half v squared by c squared, which is roughly m naught for small v by c. So, that means in writing the correct equation, we are not completely dismissing the Newtonian laws. After all, we know that they work extraordinarily well in the laboratory scale, in the terrestrial scale. That is because this v by c is a very, very small quantity. That is what we have. In a similar manner, what we can do is to now write the expression for the momentum. So, expression for momentum is now very, very simple. I will write m of v into v. If I write this expression, now you see there is no contradiction at all. I can still write dp by dt is equal to f constant. But when I try to integrate, this m of v will also come. So, p of t is equal to f of t into t is equal to, now I will be careful, m of v of t into v of t. That means, but f of t is equal to constant. So, I should not put this at all. I am sorry about that. Otherwise, I will have to integrate that. F of t is equal to constant. Therefore, p of t is equal to f, which is a constant into t. This is the correct expression. You see, my momentum will be increasing linearly as a function of time, but my velocity will not be increasing linearly as a function of time, because p increases linearly, but when p is increasing, my mass increases, my speed increases or velocity increases. Let me put a vector sign over this, such that the linearity in p does not become a linearity in v, and as time passes, my velocity will asymptotically approach the speed of light, the velocity of light. Those of you who can do this integration are welcome to do it. It is not a very, very difficult thing, and this is something that we are going to get. This is a very important relation for us. You may be wondering why I am discussing all this in this particular set of lectures. The reasons will become very clear to you in a minute. And by the same token, my expression for energy as a v will now be given by m naught c squared divided by square root of 1 minus v squared by c squared. That is what I have. This is the famous Einstein mass energy relation, E equal to mc squared. So, if you want, I can write it as m of v into c squared. Again, if you were to make a binomial expansion of this quantity, what will this quantity be? This quantity will be nothing but m naught c squared approximately into, now I will be careful, 1 plus half v squared by c squared plus higher order terms, which is m naught c squared plus half mv squared, m naught v squared. And this you recognize to be the Newtonian expression. What was the genius of Einstein? The genius of Einstein was that he did not treat this as an unimportant constant which cannot be measured, because we know only that energy differences are measurable, but energy is not measurable. But he gave a precise meaning to this, and he said, even when the particle is at rest, it carries a lot of energy given by m naught c squared, for which actually there is an extraordinarily good experimental evidence. Is that okay? Pair production, pair annihilation, and so on and so forth. But again, if you look at processes where the identity of the particle is maintained, that is, its rest mass is maintained, what matters is only half mv squared for very, very small speeds. Therefore, Mr. Newton is again in safe place. All that is summarized in this particular slide. We shall look at it. So, the first expression is the expression for the relativistic mass, m naught into 1 over root of 1 minus v squared by c squared. By the way, this quantity is sometimes called gamma, and v by c is called beta. Do not worry about that. then my energy is m of v into c squared, I described to you. My momentum is m of v into v. If you combine these two relations together, you get a very beautiful relation, E squared equal to p squared c squared plus m naught squared c to the power of 4. Now, this is something which is very, very beautiful. I am not going to get into it, because although we got this relation assuming that m naught is not equal to 0, this has non-trivial solution even when m naught is equal to 0, that is E squared is equal to p squared c squared plus m naught squared c to the power of 4 has non-trivial solutions even when m naught equal to 0, because I will get E equal to Pc. So, if you write E equal to Pc, and if you write your velocity to be dE by dP, what do you get? This is nothing but c. That is what you are going to get. Therefore, this takes care of light also. That was the great accomplishment of Einstein when he gave this relation. This is also called mass energy relationship. So, now whatever I showed you through the binomial expansion, I want to show you through a slide so that you people understand what is happening. So, in this figure you see my beta v by c is changing. The maximum value that it can take asymptotically is 1 when v equal to c. Over a long range, my m by m naught, my mass does not change at all, and only when it hits something like 0.8, that is when the speed of the particle is 0.8 times the speed of the light, it starts increasing. Therefore, Newtonian mechanics is safe. What we want to now do is to start with this, combine it with the mass energy relation, introduce the concept of mass defect, and show you how the mass property of the nuclei can be understood, and from that how fission, fusion, radioactivity can be understood, which we will take up in the next lecture. Goodbye.